Hey guys, welcome to this video. Today is a little bit different. Today I have a guest, Lukasz Skotny, which is
Hi.
joining me right here. And we will talk today about nonlinearity, a topic which I, to a great extent, ignore on my channel, but it's very important. So Lukasz will tell us why it's important, what you can do with it, how costly it is in terms of computation power and stuff like that. And I'm really thrilled and excited for that video.
Oh,
So,
Manuel, thank you
welcome
for
here.
having me. Yeah, I really appreciate
it's a
doing
pleasure. It's a pleasure. So we did a while back, we did a video together with the cantilever beam, and the topology optimization, which you see today, is for the most part just linear optimization in general, because gradient methods is a linear approach. So we took this example and thought ourselves, well, how does it change if we maybe also include nonlinearity? And on this example, I now happily give the word to you to tell a little bit about this cantilever beam and what the nonlinearity part of this can do.
Okay, so nonlinearity is incredible in many ways, obviously, and I really enjoyed this. It's not like, first of all, I'm surprised that you would call this thing a cantilever, because cantilever for me is like a straight line.
Yeah, right. That's because of the design space. The design space was the straight line. And
okay. so it started as a cantilever. I will give you that. So I think that even nowadays, a lot of FEA is done in linear way. Like if you do topology, but like even in design space, because like, let's be honest, I don't think that you could do like topology optimization in a non-linear way effectively. Like the computing time would be just insane.
Yeah, you can't do it with gradients, and so it's
So most of design is done in linear way too, and I'm a big advocate that doing things in a non-linear way makes it easier for you. It's safer. It only requires some knowledge, and I'm not saying that it's simple. Like most engineering things, actually, if you go deep enough into something, it turns out to be way more complicated than you initially assume, right?
Yeah.
So nonlinearities are tricky for sure, right? But if you actually get it and you go beyond the threshold of what can potentially be done, it's incredible. So I'm happy to talk about nonlinearities all day, I guess.
Yeah. And I'm thrilled to hear it.
Right. So when you do design, first of all, you should consider two things. Like, for me at least, that whether the geometry will be linear or non-linear, or material will be linear or non-linear. And if you work at university, there will also be a third consideration, and that is contact. And like, if you really like semantic discussions, you can go to like whatever science conference that goes with computational research and discuss whether the contact is linear or non-linear. Can it be linear? Can it be non-linear? And so on. It's like the semantics of the thing is like pretty complex, but realistically speaking, contact can be a problem. And in nonlinear analysis, the convergence is a bit more tricky than in linear analysis. So it takes more time. But in itself, it's just like, two things touching one another, right? It's a solvable problem in some sense. And when it comes to nonlinear geometry, like, regardless if contact is linear or nonlinear, there is a button which says, please use contact, right? And there is actually a button which says, use linear or nonlinear geometry. So you can kind of like, switch it off, switch it on in some sense. And with contact, it's just there. Like it may require a stronger definition perhaps, but it's always there. So regardless how you call it, it's not a thing, right? So with nonlinear geometry, it's like how things move and how this movement impact the solution in some sense. So if a structure deforms a lot, this deformation will influence how much more deformation will happen later on. So the shape changes, and you kind of like take this into account step by step by step. And there are many famous examples. My favorite one is like a laundry string. Like if you have a very small string and you just attach it to two walls and hang like wet laundry on it, Like if you would treat it as a beam and calculate the bending moment and cross section of the string and so on, like there is no chance it would work. But in fact, it just deflects bending, like making an arc downward, and it gets longer and longer. This elongation causes tension, and this is how it works. And this is like a perfect example of nonlinear geometry, that if you do linear analysis, you'll just get a bending moment of insane amount, and it doesn't work. So
I cannot withstand that,
I would say that nonlinear geometry is like a silent killer of nonlinear FEA, because you never expect it. It's like when you have nonlinear material, it sends a very distinct warning signs. For instance, like I usually work in steel structures. So let's say that you have a material that yields, and at certain level, everybody knows that the yielding happens. So when your analysis shows you stress is higher than yield, you instantly know that something went wrong. Right? And with nonlinear geometry, if you don't know what to look for, it's very easy to miss this. Like you just get outcomes. Nothing outrageous happens. Of course, in extreme cases, you can get a situation where the structure deforms few kilometers, right? That would be a good indication that something like didn't necessarily work out well, right? But those are of course crazy instances. Like you don't expect this to happen in like normal circumstances. So nonlinear geometry is easier to miss, and this is why I like it more. It's like subtle. But if I would want to convince someone to use nonlinear FEA in general, I would sell it mostly on nonlinear material, because you can just say, hey, are you like fed up with the fact that you always get stresses higher than yield and everybody yells at you that this is a wrong design? There is a setup that allows you to solve this problem in one move. And okay, computing will take more. You will have to learn a bit more how FEA works, how to iterate solutions and so on. But at the end of the road, there is a button and a certain setup you can have, and you press it, and there are no stresses higher than yield. Like you're done. It works. Right? You don't have to deal with this anymore.
Well, let me maybe quickly point out the question here, because you may have with nonlinear materials no stresses higher than your yield, right? But then you will get deformations larger than with the linear, right? And so, from my experience, also the distorted elements is a huge problem then. So maybe you did a linear approach, it works, shows stresses over the top, then you do nonlinear and the simulation even does not converge, right? Did you have also that problem, and maybe can you learn a bit about that?
Yeah, the convergence is like if you're doing nonlinear FEA and there is one FEA monster, it would be a non-convergence dragon. I mean, like, seriously, like, non-convergence means so many things at once that it at some point just it's like a meaningless punishment of nonlinear FEA. You just run the analysis, non-convergence pop up, and you suddenly learn you're a bad person. This is like the baseline of it. So, of course, like distortion of elements could cause non-convergence. Of course, but in design space that I work in, distortion of elements isn't necessarily the biggest problem. I mean, if I would do forging analysis, where you like plastically deform element extremely, let's say, then absolutely, like that would be a nightmare of adapting remeshing and doing wonders with like hyper elastic stuff. If you press it hard enough, would do funny things to elements.
Something like that.
Exactly. But like in normal design, you don't necessarily get non-convergence out of element distortion, unless of course you figure out that, hey, I would just press this beautiful mesh my model quickly button and I'm done, and then I would press calculate, and like you kind of earn the right to get mesh distortion this way. And
or if you made stupid design decisions, that's also a possibility, right?
That's
it's not always a calculation.
I think that this is also the biggest problem with nonlinear FEA, because when you know how to run a nonlinear analysis, you instantly think about yourself as an expert in the field, like how fancy GIF files I can generate from my solver, right? And then if you have problems with the basics, like you do poor meshing, like you become blissfully unaware that there are basic things that you don't know because you
Yeah.
already do the more advanced stuff. So I would rather
Mhm.
like teach someone who never did FEA than
Mhm.
someone who thinks they are already an expert, because it's hard to
Mm.
sell somebody the idea, look, like you do mesh, that's okay, but like you really need to pay attention to stuff, right? And there's like,
Mhm.
no, like I'm doing like this explicit crash tests, like I know what I'm doing. And I was like, maybe like
Yeah, maybe.
experience tell me that it might not necessarily be true. And it's very
Yeah.
hard to convince someone on this level that the basics like meshing,
Mhm.
how to load model, how to support it,
Yeah.
like all those decisions are actually more important than nonlinear analysis in itself. Because if you have a
Mhm.
stupidly supported model, the most advanced
Mm.
analysis will still give you stupid answers, right?
Yeah,
But
right.
to get back to non-convergence, in nonlinear
Mhm.
analysis, you usually, like in structural design that I do, you usually face
Mhm.
two challenges. Like the first one would be that the model is simply too weak.
Mhm.
Imagine you have like a beam, you can load it to 100 kilonewtons and it will break. And
Mhm.
nonlinear analysis will see that it's breaking, right? And you
Mhm.
try to apply 200 kilonewton on it. So you apply
Mhm.
the load piece by piece by
Mhm.
piece, you get
Mhm.
to capacity, and
Yeah.
suddenly you ask the solver to apply more load, and it's impossible because it's
Yeah.
failing, right?
Yeah, it's
And then
failing,
the
yeah.
solver say, mate, this ain't gonna work so easily on you in non-convergence, right?
Mhm.
There
Mhm.
are, of course, ways you can deal with it, like arc length methods and stuff, but it's
Mhm.
a bit more advanced in this. So I think that one of the, outcluding the bad model setup, which can generate
Mhm.
insane amount of
Sure.
non-convergent errors on its own,
Yeah.
like assuming that you have
Yeah.
the model right, the too
Mhm.
small capacity would be like one of the main reasons
Mhm.
of non-convergence. And the second one would be if something yields too quickly.
Yeah.
Like there are internal checks during the calculation in most solver that would tell you something like, hey man, like the yielding rate is like crazy, like slow down
Mhm.
boy, and
Mhm.
like you need to reduce the step you increment loads and make it more
Yeah.
accurate. And at some point you just yielded the model so much that the solver is like, nah, I'm not doing this anymore. It's like
Yeah, is this a way of finding out how much load a structure can hold,
yeah, it's
basically?
definitely like that would be the best method to do that,
Mhm.
because it's also the most dangerous one, because if you make stupid assumptions you will get
Mhm.
incredible outcomes. You
Wrong
can basically
results, right?
generate any outcome you might want if you're not sure what you're doing.
Oh,
Just
that's
click around,
dangerous.
and
Yeah.
yeah. And
Change the
but
settings until this gets
I'm
that, yeah.
sure that the topology optimization is the same. Like if you're optimistic
Yeah.
enough and not sufficiently trained, you will get whatever you want. It's just a matter of how much time you have to click the answer through, right?
Yeah, and
Uh,
you're uncertain about if it's really holding. Because you get a beautiful structure, but if you have a garbage input, the structure
exactly,
in
right?
real case, it will just break. Yeah.
Yeah. So,
Mhm.
but if you know what you're doing,
Mhm.
oftentimes nonlinear FEA is the only reasonable way, in my opinion, to
Mhm.
check if something will hold, apart from testing it.
Yeah.
And the funny thing with tests, as you surely know, is that everybody believes in test outcomes apart from the guy who did the test, and nobody believes FEA apart from the guy who did the
Yeah.
FEA.
Yeah, that's common, yeah.
So there is this aspect of it that you need to be like
Mhm.
very certain of what you're doing to convince someone, but
Mhm.
it just allows you to check everything that you need. It's not
Mhm.
obviously easy from the get-go, but the
Yeah.
possibilities are just infinite. Like you can do whatever you want, basically.
It's most accurate. That's the thing. Because you just have less failure in the setup in general, because you don't know. If
Yes,
you just do a linear analysis, you don't know about the material, because you know the material behaves differently than you're assuming it linear, but you don't know how. And if you do it
absolutely.
nonlinear, you have a much more precise model, and
Yes.
therefore can
And
make much more precise assumptions and
I think that
answers. Yeah.
true. I think that what people don't realize is how much they are guessing when they are
Oh
doing
yeah.
FEA, but they don't do nonlinear FEA. Because like
Mm-hmm.
what you do is like you guessed that the geometry is linear, that the material is linear. You guessed a lot of parameters of your model. You pressed play, you got a nice picture, and now you're guessing if this is okay or not. Like if you would show someone a piece, and let's say somewhere there are stresses above yield, and by the look of it, an experienced engineer could say this is not a problem. And if you said, okay, how much higher the stress could be for this to become a problem? Because obviously there must be a limit, right? Nobody knows. Like like you cannot calculate that. So at some level, let's say, like, can I increase the load 10%? 20, 30, 40, 50. Like, there must be a limit.
Where's the boundary?
Right?
Yeah.
And nobody knows where. And when you do nonlinear FEA, like you just do the analysis, and the outcome clearly shows you what the outcome is. Like there is no guessing, there are no assumptions. So in this way, it's not even that the internal mathematics is like more accurate. It's more or less like you don't have to guess the outcome. You actually obtain an outcome that is like like a number you can use to say, like, 20% higher is too much, 10% lower is okay, and not I think that 10% more would be still okay-ish. So that's the part where the accuracy really kicks in. Like it's you who make the error, not the software.
Yes, yeah. That's great. Just a thought which came to my mind right now was you have some certain calculation which aim to implement the plastic effects, like the Neuber calculation, right? So you take a linear stress in there, and then you assume how much, if it's a problem, how much your margins of safety are, getting tackled by that. Is that how do you compare that to the real deal, right? To do the nonlinear analysis compared to the Neuber calculations.
I must say that Neuber calculations must be one of the most overused theorem in engineering.
Yeah, I think they're used pretty often, right?
Yeah, if you think about it, what it says mostly is that if you have like a beam with a notch, and you know the dimensions of the beam, you can actually guess like how the stress will average out over a notch, right? But it doesn't describe all possible phenomenon. Like let's have a plate and a stiffener that strongly ends. Like it's not the same notch, right? So the problem with Neuber rule is that there is a formula, and formulas have a tendency to accept numbers. And FEA have a tendency to generate numbers. So if you do FEA, you always get numbers you can put into Neuber's formula, and it will always spill out some sort of an answer. It's a closed, self-fulfilling process, right?
Okay.
But if like for me, like I'm not saying that's stupid. I understand why Neuber formula is great for certain applications, but it's definitely overused. And like, while they say that when you have a hammer, everything looks like a nail. I've been doing nonlinear FEA for like 15 years now. Like I have a PhD in shell stability and stuff. So to me, everything is nonlinear. I just look at the reality this way, right? And I'm not saying that like if you're doing like a doghouse or like a small dollhouse for your daughter, you have to analyze every nail with nonlinear FEA. That's not the point, right? But if the stakes are high, and the task is complex, I would never depend on Neuber's formula for anything, basically. I would just say, okay, there are so many things that I'm missing that I just have to assume that it will work. And this is how I would approach it, I think.
So it's also dependent on the load case and how...
Yes, on the structure itself, right?
Stability,
And then, funny enough, who's supposed to make a judgment call of when you can and should not use Neuber formula? It's you, right? So if you say, I know how to do it, I will always do it, then like, okay, you can, right? But it's your call to use it, right? And sometimes it might not be the best move. So I understand the need for it, and it has a lot of uses, for sure. Right?
Yeah,
but
sure.
Like, I would just be like, careful to use it as it was intended to be used, and not just say, oh, I have this fancy formula that suddenly do nonlinear FEA from linear FEA. I mean, like, come on, if there would be such a formula, there are many companies who would sell you like FEA linear nonlinear packages that
Mhm.
are so much faster than the industrial grade nonlinear solvers that they
Mhm.
would already be the most popular solution out there. It's not so
Mhm.
easy.
Right. Yeah. Okay, that's a good point. All right then. Should we jump into the model? And
Oh yeah, let's do that.
let's
I'm
get
actually
into the
happy.
detail.
So right.
Yeah.
When we finished our previous video, we talked about the cantilever, and like in good faith, I won't call it a cantilever. I will call it a
Yeah.
fin.
Yeah. All right. All right.
At this
It's
point,
perfectly
I
fine.
think it's fair. I think it's fair.
It's
Right. So
fair. Yeah.
before we even start, the first troublesome thing with topology optimization that we encountered was like meshing this was a nightmare, because
Yeah, I think
you
so.
obtain a beautiful geometry and nothing fits. You have to cut this, like make all those
Yeah.
small adjustments, like, and if I would be a guy who would have to manufacture this, like I would cry in blood.
I think so.
But
Yeah.
of course you can 3D print it, and there are other ways to deal with it. I
Well, it
understand
was
that.
generated, right?
Of
It's
course,
not
of
done by
course.
a CAD engineer. Don't.
Of course, yes, it
Yeah.
wasn't like, but like the sheer complexity, like it looks so simple and so innocent, right? And
Yeah.
there are so many round hollow sections with slightly different like diameters and thicknesses crossing over, that it's
Right.
like beautifully complex if you go into details. And sadly, those details are actually needed when you do analysis. So that was the
Yeah.
first part. But if I recall correctly, the force at the top was like 100 kilonewtons maybe when you generated the model, right?
I think so. Yeah, I'm not
I
quite
wrote
sure
it in my
because
notes that it was, but like I also know that if I recall, if you did higher or lower load, it would basically lead to a
for the
similar
yeah, topology optimization doesn't care about the amount of load if it's just one load. Yeah.
Okay, so I know that we'll get the same. As we discussed, just to have the thing straight, like this is pinned connected at the end, and it has
Right.
6 ends. So yeah, and then when it comes to the load, there was 1 point load, and at this point we had basically 2 choices to make. And well, I could choose from 2 options at least. The first one was I could apply the load directly at the edge of the structure. Like if you think about what you did in topology optimization, like there was a brick and there was a load like exactly at the end. Like that's not very cool for the pipes there, but it was doable. But just to like show some other options, let's say, I also loaded it in the
quickly.
axis.
That was this one, right?
Yeah, exactly.
Yeah. Okay, as you see that.
So what we decided is like we'll move back and forth between applying at the very edge and applying in the middle of the axis of the pipes, just to make it more interesting. And it's funny thing is that this is like one of those super small decisions that seem very innocent, and like it nicely shows what nonlinear FEA is all about, and those small things count, right? So regardless if I could set up the entire analysis, like this small decision that is not even connected with FEA in general, it's just like should I move the load slightly, will actually impact the outcomes. So without a doubt, working with nonlinear FEA produces beautiful GIF files, and that's like I really love animations like that. So this is how the failure mode would look like if you apply force at the very tip on the right. So this is how the model fails. And while this really does look awesome, and it's a good way to market your skills in nonlinear FEA and find customers, it's actually not an outcome. I mean, like from this beautiful graph, you don't know if this works, if it doesn't work. It just looks nicely. Right. So of course I could say, okay, the stresses on the last converge step look like this, and I could tell you that at last converge step the load was like 20 kilonewtons, right? So this would tell you, I don't think I would like my structure to look like this, right? But it still in some sense is not an answer, because if I would say, okay, and 15 would work, like this picture doesn't tell you that, right?
Yes.
Of course, if you would like to have a numerical value, you could say, right, the stresses, like I assume the simple bilinear steel, so it's like an infinite plastic plateau. You could do the strengthening, but it rarely changes anything reasonable. So
yes,
like the stresses obviously are at yield. So Like, it's not an answer. Like, you could press a lot harder and it would still be at the yield. Right? So what you can check actually is plastic strain. So how much plastic deformation you get in your element. And this is where this becomes pretty scientific and engineering-wise happy, because there is a practical limit to how much plastic strain you can allow. And there are a lot of codes in various industries that would tell you that in our type of structures, we allow this much plastic strain. So you just say, okay, let's check how much plastic strain I've got. I've got this much, this is allowable. And you can tell, like, literally it's 78% capacity in some sense, right? So that would be a very useful trick. But the real answer comes from the chart like that. It displays on the vertical axis the amount of load that I applied. It's in like percent, but without percent. So like 0.15 means 15% of the load. And the load was 100 kilonewtons. And on the horizontal axis, you see deformations of the tip downward. So basically at the beginning, you can see that it nicely go linearly upward. So I applied a bit of load, deformation happened, more deformation, and so on and so forth. Obviously, this also tells you that this analysis produces gigabytes of outcomes, because like every load step is like a second, like an analysis you have outcomes for. So you can use each, like you can display each of those independently, and this is why I can make an animation of that.
Yes.
Right? So not only it computes long time, but like you also have to have like big hard drives to store this. And then at around 20% of the load, this is why I knew that the capacity is like around 20 kilonewtons. You can see that this line becomes horizontal. It basically tells you the model has enough. Like it won't carry anything more. And if you would press harder and harder, the line will just go horizontally till you will reach huge plastic strains. And this clearly shows you what the capacity is. Of course, if you would like to really geek out about nonlinear analysis, there are ways to analyze those charts to receive like a numerical value of what precisely the capacity is. Like it's a bit theoretical, so I don't want to go so deep into details there, but it's doable still. So in the end, like you don't have to worry of, oh, I've got a stress concentration here on the connection that says 278 megapascals. Can I allow it? You just derive the proper answer from your model. And now, to see how the small assumption where the load is on the tip or in the axis change the outcomes, this is actually how the failure mode looks like if you apply the load in the axis of those pipes at the end. So it's a small eccentricity, but as you can see now, it's like the bottom part they're failing, and it really goes under severe deformations. And this is how stress state look like. You can also see that it's nonlinear analysis if you know what you look for, because the pipes are deformed in a weird way. They are empty inside, so they kind of like lose the round shape and they become elliptical in many places depending on the direction of the bending and so on. So, so you actually can see that the outcomes change. And of course, to me, again, more interesting would be plastic strain. In the last converged step, those are actually pretty high, like 6.6% of plastic strain would not be allowed in most codes. Like usually it's like 5. I like to be like around 2, 3 maybe. The funny thing is that usually if you would allow twice higher plastic strain, this doesn't mean at all that the capacity of the model is twice as high. In fact, it's only like a very small part, because if you look at the buckling, the equilibrium path, it goes upward and then it almost goes horizontal. So the load is not increasing anymore, but the deformation is increasing like crazy. So you don't get a lot of for every like 1% of plastic strain you allow. And this is why I usually tell my customers, look, like we can increase the capacity by 2%, but the reliability of the solution like is like half worse. Like, do you really want to go this route? Like, we can optimize this way for sure. Sometimes it even makes sense, but in most cases, like risking makes no real difference, because like 1% of the load or 2% of the load, it's not the price you want to chase when you decrease the capacity of the structure so severely. And but you know, it's a choice you can discuss. Like you can show, look, Like we gain 2% capacity, but the plastic strain are so much higher now. Like there are numbers you can put, like checks you can perform. And I think that this is the true magic of nonlinear FEA, that you just don't have to guess anymore. You just do it. And I do realize that doing like let's call it a cantilever. Doing the cantilever like that, it's like super
it's
useful.
catchy.
But yeah, it really is, right? But if you look close enough, it fails in a super complex way. And frankly, it's like a bit of pipes welded together. Like if you think about it, right? It's
And
a
same
relatively
material, right?
simple. Yeah, it's the same material. Like I think that at some that thicknesses of those pipes is like extremely close to one another. There aren't differences. So a lot of simple things happened, but like if you connect those, the failure mode is actually quite complex. And
right.
to be fair, if I would foresaw that the failure mode would include crashing of this connection there, with one of the pipes being so crushed that the plastic strain are too high, like you cannot really make manual calculations that would prove this, right? And if you do linear FEA, you would just get 7,000 megapascals there. And what would you do with this outcome?
Don't have
right? Like,
idea.
you don't know what to do, right? So, so actually, nonlinear FEA helps you solve most of those difficult problems, and it makes things easier. So it's more work to do it, but then less work to prove that it actually makes sense. And of course, it has like enormous amount of industrial potential, and produces really nice GIF files apparently.
Yes.
So you can
really
design
beautiful.
it's like, but I must admit that when topology optimization does its thing and you see this change,
that's also pretty nice.
It's also pretty nice.
Yeah, but also
I think that
dangerous if you don't know what to do.
Well, nonlinear FEA is the same. Like I can really produce a very stupid GIF file and it would still look really nice, right? So
everyone applauding, yes.
Exactly. Yeah. So you can design silo structures. Like since I work with shell stability, this is mostly what I do, obviously. But
pretty cool.
Yeah, it's like you can solve very weird cases, like when you have tanks with very weird imperfections that are higher than allowable. You can actually force those imperfections into your model and simply check if the model will be okay. So you don't have to convince anybody. You just have a proof, like literal proof that no, it will work either way, right? But of course, you don't have to work with shells. You can design all type of stuff and equipment with nonlinear FEA. And if things are like complex instability or difficult to predict failure mode, there were a few cases when nonlinear analysis showed me a failure mode I would not predict if I would be doing hand calculations. Like I knew several, but I missed one, and it happened to be a very important one. And then you look at the outcomes and you feel like, oh wow, I would miss this one. And it really like if you set up your model correctly, it really helps you a lot. So so obviously you can do a lot with nonlinear FEA, and it's fun because it just produces beautiful GIFs and make you a chance to convince someone that your work makes sense, that it's not a guesswork. Like imagine like a asthma verifier, and you get like stress this much higher, and you call him and it's like, like what do you even
couldn't be
yeah, and here you just have like a proof, like look, it works. And at the end, what I want to say is that learning is always fun. But it's like you need to know what you want to learn. You cannot learn everything, and it's sad because I would love to learn everything.
Time is a problem.
Yeah, exactly. Nonlinear FEA is actually cool. So when you start working with it, like everything is overwhelming, and that was my PhD. My thesis tutor came to me and said, like, "Hey, Lukasz, you're doing a PhD, so you need to do FEA. Like, without FEA, those tests will be like." You have to do that. And my first thought was like, oh no, matrix operations. Like this was the first
fun
thing
stuff.
Yeah, exactly. And then you learn a bit. And like it's a very dangerous place to be because you think you kind of like cracked it. But like there are things that are missing, so I'll be very careful there.
There's a name for that. You know the name for this
the Dunning-Kruger effect?
No, I learned it about it's called Mount Stupidity, because you have this learning curve and you gather
Yes,
experience at the
exactly.
beginning pretty fast, and that's the Mount Stupidity, because you think you
Yes.
know something, and then comes the
And then you
disappointment.
crash down. Yes, that's the Dunning-Kruger effect, the classical thing. I really
Yeah.
love it, right? So
Yeah.
when you end up on the other end, you kind of like know your way around what you do. And this is a very nice place to be. You can also notice that the guy who did those drawings for me knows me well enough to know that I get fatter and fatter.
Well,
So
Corona is also partly an excuse, maybe.
maybe that he did it before.
So it's a true wizard.
The good thing is that I'm optimistic at the end.
Oh,
you
yeah.
can get slimmer back. So I'm still working
Yeah.
on it. But the reality is that if you reach a certain level in FEA, it opens a lot of options, because so few people understand it deeply enough that the field of study is not a problem anymore. Because if you know how to use the tools right, they will teach you the rules of the industry. And it doesn't really matter if you design a plane, a ship, a car, or cargo train, as long as there is someone who knows all the rule set of this is allowed, this is not allowed, this is how we do stuff. You can model it, you can verify it, and show the outcomes, right? So it's a very powerful thing. And frankly, this also allowed me to design pressure vessels. I'm a civil engineer by trade, so technically I shouldn't start with mechanical design, right? And at some level I was sufficiently good with nonlinear FEA that there were people interested to train me in how the rule set of pressure vessel design work, just so I can do that for them. So it's a powerful thing. And if anybody watching us would like to learn more about FEA, you can join my free course, and there are 10 most important lessons I've learned during my 10 years of working in a field. It's actually more than 10 now, but I think that it's fun. And maybe one day you'll be an FEA wizard. And it's a nice place to be. It's a good place to develop in. So
and also there's a high demand, right? So so it's definitely a good thing to learn. And also I can recommend exactly that course. That's the way I got to know you, Lukasz, at the beginning. I think I watched a video of Tony Abbey and you together. And then I jumped over to Enterfea and also did the introductory FEA course, and I find it really pretty damn cool. And also I learned a lot of that. Yeah, so I can definitely recommend that. And also what I want to point out as well, your drawings are really killing. I really like the drawings. Well, you always have these little drawings, and that's so super great.
Thank you. Obviously I cannot take credit for everything. There is a professional doing the FEA wizard stuff. I would die trying. but the small ones I actually do do myself. So thank you. It's so nice to hear.
It's really,
thank
really
you for
cool.
the recommendation.
Yeah, no, really, that's from my heart. It's a really cool course, and I enjoyed it very much, and would recommend it to anyone on my channel to also sign up. It's free. You can learn something, and it's pretty damn well written, and so check it out.
Thanks, and thank you for the invitation as well. It's such
so
a pleasure to be here, man.
It was so cool to talk to you about the nonlinearity and maybe get to know a little bit of this field. I know it's a huge field, right? And maybe we will come back together and talk a little bit more, maybe on a YouTube live, for example.
Yeah, I would love that. That would be so cool.
I think there's so much to learn, and really also I think we both like very much to learn new things, and I also think so do our viewers, because while you're here listening to us two geeks talking about nonlinear FEA, where you could have a beer or something right? So
exactly.
We will be looking forward to that. Thank you so much, Lukasz. It was a
thank
pleasure.
You for the invitation, and thank you for watching too. I really appreciate that as well.
Thank you, viewer. Thank you especially, and we will be looking forward to do something together. So it has been great fun. Thank you. Bye, guys.
Yeah, bye. Take care.